Okay. So already we are about 15 minutes late because of technical problem. Anyway, so I think we have almost 2 weeks gap, right? So I hope not be remembering what we were looking at. But so this is lecture 4, and we were looking at codecs. So out of this picture here, so the first thing, how to design the codec, especially encoding decoding device. Uh, Basically a software, that will do the job. So whenever we want to store data onto DNA, we encode it, then we synthesize using synthesizer, the machine. Then we store either in a test tube or the different storage medium. You can retrieve it, and then sequencing means reading the data back, and then finally decoding. So encoding decoding is required for various reasons. For example, you want to maximize the information density. Also, you want to correct any errors that may occur. For example, reading error, writing error, or storage error, right? So for that, we have to look at, we have to use a branch of uh, mathematics or computer science known as coding theory. So we talked about error correcting codes briefly. If you remember the last classes, so whenever we want to encode yes as a 1 bit, we repeat it 3 times, and 0 as 000 3 times, and this code 000111 was able to correct single bit flip. If 0 is flipped to 1 or 1 is flipped to 0, you will be able to correct. Why? Because the distance of this code is 3. The pairwise distance between these two strings is 3. So if D is 3, 3 minus 1 by 2 is 1. So we can correct single error. Okay. If we want to correct 2 errors, we need to repeat it 5 times, right? Then because the distance will be 5, so we will be able to correct 5 minus 1 by 2, right? Which is 2. So this is our basic mechanism. So essentially, these codes are nothing but, so this is a simply a, so we are looking at certain binary strings of some length. So code is nothing but, loosely speaking, a collection of binary strings of some length is a code, right? So from mathematical point of view, we can say that if you look at the space Z2 raised to power n, Z2 is a binary field 0, 1. Z2 raised to power n has 2 raised to power n elements, all binary vectors. And if you take some vectors out of it, that collection will be a code. So code is simply a subset of Z2 raised to power n, right? So let me revisit. So this is our Z23. So there are total 8 vectors. I can take any, any collection of vectors. So simply that will become a code. A code is called linear if it is a subspace, because Z23 is a vector space over Z2 of dimension 3, right? So if you look at a subspace, for example, we may have, this code has a basis 111, right? 111 will generate all the 2 vectors when lambda is 0 or 1. Lambda times 111 will give you 000 or 111, right? So this is a one-dimensional subspace. So linear code, we denote it by NKD. N is the length, K is the dimension of the space, and D is the minimum Hamming distance, right? That is the code. So let me. Yeah, so we have here. If I look at binary code, Z to N is all vectors of the form x1, x2, xn, such that xi belongs to Z2. This is our n-dimensional space. A code is simply a subset of Z to N, a subset, and code is described by N, which is length, capital M, which is size of C, means number of code words. and D is the minimum Hamming distance. So basically, I have just given you the definition that a code is simply a subset of the whole space, right? Just collection of binary vectors. So you can do encoding, decoding for these kind of codes as well, and these are known as non-linear codes. Why they are non-linear? Because if you take two vectors out of this set, their sum may not belong to the same set. Okay, so then this is a non-linear code. Then we can describe linear code. So linear code is simply a k-dimensional, say, subspace. For n. This is described by n. Note that now the k is the dimension, n is the length. So we described it, this code C by length n. K is the dimension of the space and D is the minimum Hamming distance, right? So I've given you, for example, C is equal to 0, 0, 0, 1, 1, 1 is a 3, 1, 3 code. 3 is the length, 1 is the dimension because there is only one vector in the basis. D is the 3 here, right, in that case. So as I mentioned, C can be described by two kind of matrices. Generator matrix, I already gave you an example, K by N. So basically, if you look at C is a subspace, it will have a basis. You write down all the basis vectors in the form of a matrix, you get a K by N matrix, K rows and N columns, right? This K by N matrix, I can give you a standard form because all these rows are linearly independent because the dimension of the space is K. So all these K rows has to be independent. So we can denote it by IKA for some A. Okay, this is known as standard generator matrix, right? I also gave you an idea about, so C can be described, so linear code can be described by a generator matrix having K basis vectors which will span the whole space. And how do you span the whole space? So C is linear combination of all these independent vectors, K independent vectors, right? So linear combination, lambda 1, lambda 2, lambda 3, and lambda k are from ground field Z2. Z2 is having only two elements, 0 or 1. How many vectors will be there? 2 raised power k, because each choice of lambda will give you two possibilities, right? So 2 into 2 into 2, 2 raised power k. So cardinality of C will be 2 raised power k. Okay. In case of a linear code, dimension of C is k, so cardinality of C is 2 raised power k. Now, we can also describe a linear code by a matrix known as parity check matrix. So, in fact, it is something like this. A matrix of the form K cross N is known as parity check, N minus K cross N. It's a parity check matrix. It's a binary matrix, I'm assuming. It's a binary matrix, right? So code C is defined by all those vectors X in D2 raised to power N such that Hx transpose is equal to 0. Null space of this matrix H. Okay, this is another description of the code. So I will give you an example and show you actually now how do we construct this. So let us take one important thing to note, that if generator matrix is of the form IK A, then parity check matrix H is minus A transpose, H is minus A transpose I n minus k. There is a formula. So if G is given, I can find out H like this. Okay, this is n minus k cross n. So what is the rank of G? What is the rank of G? Anyone? Rank means how many linearly independent rows or columns. What is the rank of G? It's a k by n matrix. K rows, n columns. What is the rank of G? K, because there are k rows, right? And all are linearly independent, right? You can clearly see that because there is an identity matrix here, right? So all rows will be independent, right? So rank is k. Okay. And what about rank of H? Because of this matrix, obviously it is n minus k. Because of this identity matrix sitting here, right? So all these, so the rank is n minus k there. And there is a relationship that GH transpose is equal to 0. You can compute that. Okay. So now let me take an example and I'll show you. Last time I have shown you from G, we have constructed H. Okay. Now actually, if I have that slide here. Okay, I think. Yeah, I don't have it here. No problem.
Okay.
That is taken.
Pixel okay. Hello. બસ થઈ ગયું. Okay.
Hello.
એટલે આ ડિસેબલ હતી એમ ને? ખ્યાલ આવી ગયો. હા.
Okay. So
ના એ તો પેલું બનશે ને સિસ્ટમ. હવે આપણે મારી વાત. હા એક્ઝેક્ટલી એક મિનિટ ચાલુ રાખજો. ફરી કરીએ પ્લે. હેલો ફરી પ્લે કરી દે તું.
रमेश भाई आपकी आवाज आ रही है, बंद करिए अपना माइक.
ओके सर.
Anyway, so let us take an example here. Generator matrix is 1 0 1 1 0 1 0 1. Okay, 2 rows. So from that G, I can find out how many vectors will be there. So take first row 1 0 1 1. So lambda 1 times this plus lambda 2 times this second row, and take the linear combination. So lambda 1 is 0 or 1, lambda 2 is 0 or 1. You will get all these 4 vectors, right? Clearly, right? So from the basis vector, I can find out all the 4 vectors. This is our code C. Okay, this is our code C. Now, from that formula, you know that G is I2 bar A. A is 1 1 0 1. H is minus A transpose I n minus k. So can you find out that H is the same thing what is written there? You can clearly see that H is that from that formula, right? 1 0 1 0 1 1 0 1. So I n minus k is 2, I2 here, right? Okay, in that H matrix. Now, let me show you. So H is your 2 by 4. So this is in general n minus k cross n. If n minus k is 2 and n is 4, so what is k? 2, right? So basically, remember I gave you the definition that C is nothing but all x in e2 raised to power n such that hx transpose is equal to 0. Let us see if this is the case here. So what I'm going to do here now, 1 0 1 1 0 1 G is equal to 1 1 0 1 1 0 1 0 1 0 1 1 0 1 0. H is your 1 0 1 0 and 1 1 0 1. Right. So let us find out C. So I know from this C is what? I have written all the 4 vectors here. 0, 0, 0, 1, 0, 1, 1, right? And 0, 1, 0, 1, last 4 vector, 1, 1, 1, 0. This is C. By taking the linear combination from G, I can get C, right? Now let us look at the other definition. So C is nothing but Hx transpose such that, sorry, all those vectors x in 2 raised to power n such that Hx transpose is equal to 0. So I would like to find out C from H and see whether we get the same thing or not. So what I'm going to do here now, X, vector X is unknown. So I can assume that it is, what is the size of X? X1, X2, X3, X4, right? I'll just multiply 1, 0, 1, 0, 1, 1, 0, 1, X1, X2, X3, X4. Hx transpose is equal to 0 means 1, 0, 1, 0, 1, 1, 0, 1 multiplied by this. How many equations you will get when you multiply? 2, right? You can write down what are the equations. We'll get x1 plus x3 barabar 0, right? And then x1 plus x2 plus x4 barabar equal to 0, right? These 2 equations we will get. This is our H. This is our X transpose. So Hx transpose equal to 0. I have put. We got these equation. This equation. X is unknown. I want to find X, the value of X, right? And you will see that the value of X, all the vectors when we find, actually we will get C, which is written there, right? So now remember what happens in this way. K is 2. If you remember, K bits I want to encode into n bits. So this matrix H works like this. We have K information bits, right? K information bits. We extend it to n information bits by adding n minus K bits more, such that Hx transpose is equal to 0 for some matrix H. Okay, that is the way definition is, right? For the Petri check matrix. So we are adding some Petri check. So we have K bits of information. I'm adding n minus K bits of information so that the whole vector is of size n, such that Hx transpose is equal to 0 for some H, which is n minus K cross n. Okay, so if we do this, so this is our, so we have 2 bits of information with us here. I'm extending it to a vector of length 4, such that this into this is equal to 0. And so we have this. That means 2 bits, like we can assume first bit x1 and the second bit x2 is in our hand, right? So there are 4 possibilities. So that I can find out what will be, x3 and x4. So certainly x3 is minus x1 is same thing as x1, right? What about x4 is minus x1 minus x2 is equal to, now x1 is obviously this is x1 plus x2. So we got x3 is like this, x4 is like this. Now x1, x2 I can vary 0, 0, 0, 1, 1, 0, 1, 1. If I take x1, x2, 0, 0, what you will get? x3, x4. What will be the x3? 0, right? And what is x4? 0, right? From the equations, I'm just looking at these 2 equations. If x1 is 0, x2 is 1, so what is x3? 0, x4? 1. In this case, x1 is 1, x2 is 0. 1 here. Huh? And what about here? Are you sure? Are we getting the same vectors as written in C? Right? So this is another way of doing in the math. So encoding works like this. If I'm using generator matrix, k bits are there, some k bits, that is in our hand. So I am adding, what I can do if I using generator matrix, multiply with the generator matrix G, which is k by n. So these k bits will become n bits. Okay, when we take a vector of length k, multiply it with a matrix of size k by n, I will get a vector of length n. So this is where encoding works if I use generator matrix. If I use parity check matrix, what I do, I have k bits, I add extra n minus k bits such that hx transpose is equal to 0. Right? So this is the way encoding works if you want to use parity check matrix. Both have advantages, disadvantages, right? Depending upon what kind of decoding you are using and so on and so forth, right? So there are two descriptions of the linear code. So vector space can be described by the generator matrix, also by a parity check matrix, right? So I hope with this example it is clear, right? Now, what I'm going to do, I would like to show you decoding. Okay, so I think did I talk about sphere decoding or not yet? Anyway, one way of decoding is what you can do. So take this element of C, and for each code word, draw a sphere of radius d minus 1 by 2. D is the minimum distance. Draw the spheres of radius d minus 1 by 2 along each of these code words. There are 4 code words in C, and you will get a sphere, means some vectors will be there. So what will happen? You draw a sphere along 0, 0, 0. You draw a sphere along 1, 0, 1, 1. You draw a sphere along 0, 1, 0, 1. You draw a sphere along 1, 1, 1, 0. When I mean sphere, means a sphere of some radius, exactly same the way you study in mathematics with respect to the distance, right? Okay. So then you will see that these spheres are disjoint. Number one. So you can verify this on your own by drawing the spheres of radius d minus 1 by 2. So here d is what? 2, right? So 2 minus 1 by 2 is 1 here actually, right? So you can draw spheres of radius 1 here, right? So you will see that actually the whole space is partitioned into these spheres, and these spheres are disjoint. The whole space here in this case length is 4. So 16 vectors will partition into 4 spheres. Okay, and this sphere are disjoint. So that means if I send a vector x from C, some vector x from C, I receive y. Y will be certainly a member of the whole space, but the whole space is divided into 4 spheres, so it will fall into one of the sphere, right? You check in which sphere it is, look at the center of the sphere, and say that this is the actual vector that was sent. This is how the sphere decoding is done. Okay, got it? So send a vector x from C, right? We know that everything is spheres have been drawn. These spheres cover the whole space, right? I mean, kind of. So if y is received, you see which, actually not cover the whole space. If it covers the whole space, actually, anyway, forget about it at the moment. But anyway, so this is how you do the decoding, sphere decoding. Let me show you now array decoding actually. Now what I'm going to do here, so I have written C as 4, 2, 2, right? I have purposefully taken this example. The distance is 2 here. How many errors will you be able to correct? If D is 2, can you correct single bit? No, because D has to be 3 at least if you want to correct single bit. Because D minus 1 by 2 errors you can correct, right? But just to illustrate you what happens here. So what I have taken, so message is 0, 0, 1, 0, 0, 1, 1, 1, right? That is, these are the message bits. Now what I do, code C, all these 4 vectors I have written, right? So what I'm doing, I am forming cosets. C is a subspace of the whole space. I am forming cosets by adding a vector to all the elements in C. When I add vector 0, 0, 0 to C, we will get C itself, right? So 0, 0, 0, the first line here. So you can check this line here. So this line here, the first line. Sorry, first line is this code C when we are getting first line C. So 0, 0, 0, 0, right? All the 4 vectors of C getting. When we add vector 1, 0, 0, 0 in C, what is happening? It is, you are getting, so I'm adding 1, 0, 0, 0 to all the vectors. So we will getting 1, 0, 0, 0. And you remember 1 plus 1 is 0. Those kind of things will happen. So we get second row in the array. Then we take another vector of weight 1, add it to everything, you get third row. Then we add another vector of weight 1, 0, 0, 1, 0, we get another row. So all 16 vectors of the space has been divided into 4 cosets, right? So array decoding works in this way. X is sent from C. Okay. Suppose, we send this vector, suppose 1, 0, 1, 1 is sent from C, and error has happened, Suppose, and we receive 1, 1, 1, 1. So what we will do? We look at Y and see where it is in these cosets. So 1, 1, 1 is in third row, right? So third row, what vector was added? 0, 1, 0, 0. So you just subtract that vector from 1, 1, 1, 1, and you get 1, 0, 1, 1. So I will say that 1, 0, 1, 1 was sent. That means the message was 1, 0. Got the recording procedure? Now, question I want to ask, distance is 2 for this code. Still we are able to correct. How and why? Any idea? Yes. No, actually, what happens here in this case, what is happening, because distance is 2, in some cases you will be able to correct. It's kind of partial decoding is possible, right? So we are not giving, I'm not giving any guarantee that this code will correct all single errors. In some cases it will be able to correct. In some cases it will not be able to correct, right? So basically, because distance is 2. So if distance is 3, I will guarantee you that all errors will be corrected, okay? Just to illustrate you that, that's why I have taken d is equal to 2 example, okay? Just to show you. So you can obviously try your free time, take a linear code with distance 3. Say for example, C is equal to 0, 0, 0, 1, 1, 1. You can do the coset decoding or the sphere decoding, right? You can form the spheres and do and then see that how decoding works, right? So I hope you got the idea, right? This is how array decoding works, okay? Now, managing this array while decoding is again a task, right? You have to make an array in programs and do all this decoding procedure. If the size is very large, you have to maintain huge array, right? So there will be a problem. Can we simplify this procedure? So answer is yes. And the way what we do, it is known as syndrome decoding. Syndrome. So what you do, syndrome is, if X is sent, Y is received, syndrome of Y is HY transpose. That's all. And this syndrome, you can compute for each vector. For example, you see, syndrome of 0, 0, 0 is HY transpose. The definition is this. Syndrome of Y is HY transpose. You send some vector X from C, you receive Y, compute syndrome. Syndrome by definition is HY transpose, right? So HY transpose. This is the definition of syndrome. Okay, so you can see that all the first 4 vectors 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0 will have syndrome 0, 0. By simple calculations, you can see that, right? You can compute this, right? H. Okay. Similarly, if you look at second row, each vector has same syndrome 1, 1. Third row, each vector has syndrome 0, 1. Fourth row, each vector has syndrome 1, 0. So there is a one-to-one correspondence between syndrome and the kind of decoding that you want to do. Now what happens? If X is sent, Y is received, you don't have to go to the array. You just compute the syndrome. If Y is 1, 1, 1, 1, just you compute the syndrome, and this turns out to be what? If y is 1, 1, 1, 1, syndrome turns out to be what? How much? 0, 1, right? You look at 0, 1 is this one. So I just compute I look at the bit that needs to be changed, which is the second bit, right? You just flip the second bit, and you get the actual vector that was sent, right? So this is syndrome decoding. Got it? Any question? No, actually, this is not sphere decoding. This is array decoding. Okay, this is array decoding. I'm just don't confuse with sphere. Sphere I have not talked about. I can talk about it, if you want. But this is the array decoding. So what is happening? So in order to form the array, I should mention that once C is there, you start with any vector of smallest weight. So here I have taken vector of weight 1 from the whole space, and I add to everything in C. So all these are weight 1 vector. Once this is finished, of course, now the decomposition is done, right? Now, how many arrays will be there? How many rows will be there in the arrays, or how many courses will be there? That depends on the error correcting capabilities of the code itself. Because now here you see that this code, in this case, because 1 bit flip is we are able to cover, right? 1 bit flip, right? In this array decoding, right? Yeah, so actually, if you add more vectors, you will get repetition of the coset, right? C, you will get the repetition. So what happens when you start with a C and you start adding vectors of smallest weight? You will get basically coset decomposition. Okay, I am just talking about coset decomposition. Once you have the coset decomposition, so now x is sent, y is received. Look at the coset, which row you are at the top f vector. That will be the decoded vector, right? The actual vector that was sent. So I told you that this is an example where we will not be able to correct all single bit flip, because this is because the distance is 2. Okay, so we will not be able to correct all the time. This is a kind of incomplete decoding. So if you take d is equal to 3, certainly I can assure you that you can correct any bit flip. Okay, so this is the thing. Okay, I have purposefully taken this example just to illustrate that there are cases where it will not work. Right, you can find it out. So rather than maintaining array, we can also look at syndrome. This is something which is a nice thing to handle, right? So syndrome is there. We can do the syndrome decoding easily. So I think I should give you some exercise maybe. For this code, C is equal to which is subspace of Z23. Find the sphere of radius t along a vector x. Now this is actually t is d minus 1 by 2. So it is all those vectors y such that distance between y and x cannot exceed t. Okay. So now I would like to ask you, now d is 3 here. So t is what? 1. S1 0 0 0 is what? Just tell me. And the other one is S1 1 1 1 will be what? You will see that Z23 has 8 vectors. Z23 has 8 vectors, right? All those will be partitioned into 2 separate things, right? So now this is the sphere decoding example I am giving you. So now if x is sent, so say 1 1 1 is sent, and so bit is flip is so 1 0 1 is received. You see which sphere, can you compute these values? Right? I hope you can compute these values easily, right? Just computing the distance, right? So from 0 0 0, if I list down all, of course 0 0 0 will be here, right? and the other one, and so on. You can compute all with distance less than or equal to 1. So distance less than or equal to 1 from this and distance less than or equal to 1 from this will partition the whole space into 2 spheres, right? So now when X is sent, Y is received, look at which sphere it is, and they decode it as a center. So here this is the center of this sphere is centered around this. This sphere is centered around 1, 1, 1, right? You can do the sphere decoding. Right? Decoding is the most difficult problem. It's an NP-complete problem for a larger class. And there are different beautiful mechanisms purely from computer science point of view, which are used. You know, for each code, people are trying to find out efficient decoding schemes. So there are some popular ones like list decoding. You know, for codic residues, there are special kind of decoding mechanisms are there. The ones which I talked about basically sphere decoding and array decoding and syndrome decoding. These are quite easy ones. Okay. So I will give you one more example in the next class about Hamming code and how syndrome decoding becomes quite easy there. Hamming code is quite useful, has been used in all your memory in your computers. You know, so if bit flip is there, it can correct single bit flip easily. You know, so depending upon the choice of the application, different kind of codes are used. Right. For example, in your QR code, Reed-Solomon code is used, right, which is another interesting and beautiful code.